Okay, so sitting nicely on that one page there are our three standard basic trigonometric functions: sin x, cos x and tan x. Now, if we're going to use those functions to model real-world phenomena, hardly anything varies from -1 and 1. It happens to go nicely through 0, 0. So what we need are not the basic functions, but a more general version of these. Okay, so to be really useful, we need a general function. And so I say the general form of the sine function is in fact this one here. F of x is a times sine of nx plus k, where a, n and k are just numbers. When we put the function in that form, and so I'll say this is important, when we put the function in that form, we can model every sort of periodic. Oh no, I take that back. We can model a whole lot of periodic phenomena. This is really, really flexible in here. Now, again, harking back to the 3 weeks ago that you maybe have forgotten, but you'll have to bring back to memory, is if I have a function and I multiply it by a constant, that stretches the function vertically. So I'll just say here, the number a will scale or stretch, sometimes scale, sometimes compress, the graph vertically. And that, when we're talking about trig functions, actually has a name, that factor. It's called the amplitude of the function. And essentially, the amplitude is how far the function rises up above the central point. So our standard sine graph has an amplitude of 1. It's 1 above and 1 goes 1 above and 1 below, the average, if you like. So that's the amplitude. It tells you how far above and below the average it goes. And as I say here, that number a will give you the amplitude. So for your standard sine function, a is 1. Having a constant multiplying the actual argument of the function, so let me call that 2. So n will scale the graph horizontally. So you imagine if you've got a small average, pulling it out this way or pushing it in horizontally. And the amount by which it does it is given here. So a standard trig function, a standard trig sine function, I should say, has period 2 pi. If I put an nx in there, then the period goes down to 2 pi on n. In there. We'll have some examples of this as we go along, and will make more sense, hopefully, as we go along. And lastly, the constant. Now, we've actually got a constant added inside here, which is a little different. If I'd put the constant plus k right out the side, that would have shifted it up or down. But in this case, this one's actually a little bit different here because we've got the k inside the argument. And this one is called the phase of the function, and it shifts the graph. This one shifts the graph horizontally. As I said, if I put the k right out the back, that would have shifted it vertically. Shifts the graph of y is equal to sine nx horizontally. And again, we'll go through some examples and see all of this in action. But that's the general mode of operation here, in that by varying A, N and K, I can stretch this graph to fit all sorts of different things. Stretch it that way, and so forth. And as I say, I probably needed a plus C on the end to shift the graph vertically. But I'm hoping you can do that yourselves. Okay, so let's do some examples of this sort of stuff. Okay, so it says, sketch the graph of this general sine function, sine of x plus pi on 4. And remember, we're assuming here x is in radians, sitting in here. State its period and amplitude. So what we do in all of these is we begin with the standard sine graph. So start off with that one. We know the graph of sine x, and so I probably should put it back up here for us to look at. Here it is, sitting there. So I'll draw it on here, just dot it in, and I've got some lines here to help me get it accurate. So that's the graph that we would start off with. We'd start off with y is equal to sine x. Let me just in here use that notation. Let me call that function x. His sine x might be better, because this graph then becomes function x plus pi on 4. So the graph of f of x equal to sine of x plus pi on 4. Would have been better if I'd have called that g, now that I think about it. Is the graph of y is equal to sine x. Now, it's plus pi on 4, so that's going to be shifted to the left by pi on 4 units. I find a simple way to think of this is, look, I know, for example, that the sine of 0 is 0. Now up here, to get the same point, I have to put x equal to minus pi on 4. So I've got the sine of minus pi on 4 plus pi on 4, that's sine 0. So what's happening in the graph of this at minus pi on 4, which would be here, happens on the sine graph at 0. So everything has to be shifted to the left by pi on 4 units. And that being the case, then here comes my graph that I'm after, if I can trace that down. And so this becomes the graph of y is equal to sine of x plus pi on 4. Everything has, the graph of sine x has been shifted this way by pi on 4. Because this graph is g evaluated at x plus pi on 4. Now it says, sketch the graph. So we've done that. We've done that by translating the graph of sine x. It then says, what's the period and what's the amplitude? And in this case, you could do it two ways. In fact, let me do it both ways. I can just say, because we have just shifted the graph, I might use the word translated the graph of y is equal to sine x, the period and amplitude will be the same as for y is equal to sine x. That's supposed to be x in there. So all I've done, I've got the graph and I've just shifted it to the left. So I haven't changed the period, I haven't changed the amplitude at all. And so that would say it's therefore that the period is still 2 pi and that the amplitude is still 1. Alternatively, you could look at the graph and you can say, can we see it here probably? It crosses the axis here at minus pi on 4, crosses this axis at 7 pi on 4, so that thing's 2 pi apart. So there it is, it's repeating every 2 pi units. And the amplitude, it goes plus 1 above 0 and down to minus 1, so the amplitude is 1. So you could read it off the graph. Or alternatively, you could say, look, here f of x, so I'll just say or here, f of x is sine of x plus pi on 4. In terms of our general trigonometric function, a here is equal to 1, n is equal to 1. So if a is equal to 1, if a is equal to 1 and n is equal to 1, so therefore we said here the absolute value a is the amplitude, so the amplitude is 1. The period is 2 pi divided by n. 2 pi divided by 1 is 2 pi. So you can read it off straight off from the formula. So therefore amplitude equal to the absolute value of a, which is 1, and the period is 2 pi on n, which is 2 pi. And so we get the same in each case. And we're happy with that. Okay, let's move on to the next one. The next one says, you get it? Sketch the graph of, there it is, 2 cos 3x. And we're going to start this time with the graph of cos x, so the dotted one sitting there. So that's going to be the base one, and we're going to work out the graph of 2 cos 3x, starting with that one. I'll just put that there for those that want to see that. So here we go. Begin with the graph. Begin with the graph of y is equal to cos x. Good spot to start. And if I can recognise it in amongst all of this, it comes like this. And so there's our graph of y is equal to cos x. Now, it doesn't matter which order you do things in here, but I'm going to go and draw the graph of cos 3x next. So the graph here, the graph of y is equal to cos 3x. So I've now got a factor sitting in front of the argument x. I've got 3x in there. So that will be the graph. It's the graph of y equal to cos x compressed, I will say, horizontally. Because this number is bigger than 1, it actually shrinks it in this way. If that was less than 1, it would drag it out that way, horizontally, by a factor of 3. Have a little think about that in terms of common sense. Here's my cos graph. For example, I know that cos of 2 pi is 1. So what's going to happen when I have 3x is the cos of 2 pi on 3 is going to be 1, because 2 pi on 3 times 3 is 2 pi. Let me scribble somewhere. Let me just get this here and let me scribble on the back. If I have function x is equal to cos x, then function 2 pi is cos 2 pi, and so that is 1. Now what we're looking at here is gx equal to cos of 3x, and you can see that the same value is going to occur when I put x equal to 2 pi on 3, because this is the cos of 3 times 2 pi on 3 in there. And so what happens at 2 pi in the first graph happens at 2 pi on 3 in the second graph. Right? So the period has been shrunk by a factor of 3. So what I do, put that there. What I do is I go to my graph and I work out where 2 pi on 3 is, and it turns out that it's right here. There's 2 pi on 3. And so I squish my cos graph up so it fits into here. And if I do that, it now comes down like this. So I don't know if you can, that doesn't appear to show up too well. I don't think, oh no, you can see it. Here. So let me colour it in down here. Comes down, up. And so I've divided everything by 3, and there, that little bit is the cos part of the cos 3x graph. And in fact, there'll be 3 of those fit into our normal period of 2 pi. So this will occur 3 times. So let me keep going. There's the second time, and then I come down, and there is the third time sitting in there. So that's the graph of y is equal to cos 3x sitting there. So as I say, there are 3 cos-like graphs fitting inside the period 2 pi in this new function. And lastly, now I have to do the 2 part. And so I can say the graph of y is equal to 2 cos 3x is the graph of y is equal to cos 3x. So I'm building on the graph that I just drew. and I'll say stretched vertically by a factor of 2. It's interesting in here, to actually stretch horizontally, this number has to be less than 1, whereas to be stretched vertically, the number here, the A, has to be greater than 1. So that's a little bit of a trick for young players in there. So let's now stretch our cos 3x graph. And so what used to happen at 1, or at 0 we got 1, I multiplied that by 2, so now I'm up here. And so it will come down like this. And 3 of them will fit in. And so that's the graph of y is equal to 2 cos 3x. Unfortunately, the red doesn't appear to be very red on that one. Looks really nice on my piece of paper here. And so, we want its period and its amplitude. We worked out here with the second part that this has period 2 pi on 3. So the period is 2 pi on 3. And we can see from the last part that we did that the graph will go up 2 and down to -2. So the amplitude is 2. The amplitude is 2. And of course, in terms of the actual formula, in here you can see that in the graph 2 cos 3x in that function, A is equal to 2, so that's our amplitude, N is equal to 3, so the period is 2 pi on 3. 2 pi on N, 2 pi on 3. So that's our period sitting there. And there is a very complicated looking graph. But you can see in here now that I can start to manipulate these graphs to fit any sort of periodic shape. That's the important thing that we're doing here. Now let's have a go at sketching the graph of 4 tan x plus pi on 2. So as always, begin with our basic trig function. So begin with the graph of y is equal to tan x. And I've got it down here. It has pi on 2 as its asymptote. So it looks something like that. So that would be the graph of y is equal to tan x. And notice in this one, all we've got to do is find the period, because amplitude doesn't make sense in this particular graph because the range is all real numbers. So we don't worry about amplitudes for tan graphs. But so far the period is pi. It repeats itself every pi units. So again, it doesn't matter which way you go, whether you deal with the K or whether you deal with the A. I'm going to deal with the K first, but as I say, it doesn't matter. so we have the graph of tan of x plus pi on 2. Because that's a plus, it will move our graph to the left, and because that's a pi on 2, it will move it to the left by pi on 2 units. So it will be the graph of tan x shifted to the left by pi on 2 units. Sorry?
Can you slide your page down a little bit? Yeah.
Oh, you couldn't see the question. So I get this dotted graph here and I move it to the left, and it now looks like this. It goes up. We'll go up like that. So that will be the graph of y is equal to tan x plus pi on 2. It's been shifted to the left by pi on 2 units. Even though the graph's been shifted, of course that doesn't change the period. It still repeats itself every pi units. So our period is in still fact pi in this case. And now I can deal with the 4. So I can say the graph of y is equal to 4 tan x plus pi on 2. That's the graph of y is equal to tan x plus pi on 2 stretched vertically by a factor of 4. So I just get hold of my tan x plus pi on 2 graph and stretch it. And so it will look like this. And so on. So that one there is the graph of y is equal to 4 tan x plus pi on 2. And again, all I've done is stretch this thing. I haven't changed the period at all. And so the period will be pi. Yeah?
So on your cos, you were, because you had temperatures, you chose the stretching.
Yes.
So over here,
Yes. So so for example, if I took that value there, so for this value of x, that value there multiplied by 4 gives me that.
so just judge it.
How do I judge it? I got the computer to draw it and I had it sitting under there. Okay? For you guys, just do it. Yeah, you stretch it and I'll pretend it's 4. Okay? Yeah.
I see what you mean. You can judge a point of it.
Yeah.
Pick one.
That's right. If I pick that point there, go to there, then 4 times it puts me up there.
Yes, so just.
Yep. And likewise going down. Pick a point down to there, 4 times that brings me down to there. Yeah. That's what you're supposed to do. And as I said, it's super hard to do by hand, but it's really easy when you've got a computer. Yeah. And we should put down the bottom here that the period is pi, the same as the tan graph. But that's what I mean every time when I say stretch by a factor. For any point you pick, multiply by 4. And that's what we did with the other ones as well, and multiplied by 2. Yeah.
In the exams, the sketching is relative, isn't it? It's not exact. Right.
Sketch means rough, qualitatively correct.
Do we have any plotting questions?
Again, it's multiple choice. And so what I will do is I'll do the plotting for you. I'll say, here's a function, which one of these is it? And I'll actually give you some graphs. and you'll be able to say, oh, well, I know how to get that from there to there to there, so therefore it's this one. Okay? Yeah, that's the best I can do in a multiple guess format. Okay. But of course, you know, I'll have one where they'll all look similar is the problem. And so you might get confused if you don't be careful. Just before we get underway again, can I get you, if you happen to be writing these things down, and oops, I've got to do this over this side so the people at home get it. Sorry? Yeah. Okay, here we go. Way back here I said, Case, when we were talking about the general form of these trig functions, I said K shifts the graph of y equals sine nx horizontally. It might be useful if I added in here by a factor of k on n. So far, all of the ones that we've done where we've had a k, we've also had n, but n has been 1. And so it's always shifted it to the left or the right by the actual k value. Because I'm about to do an example where I've got an nx plus k. So that's the result. I'm going to try and explain why that's the result in the next example. So has everyone suitably modified what they want to modify? Yep, good. Okay, so here we go. You can see here I've got an n is a half and a k is pi on 4 here. So it's relevant to this example. So I will leave that sitting on top so we can come back and have a look at that. So, as always, it's a general trig function. So start off when you try to draw its graph by looking at the basic trig function. So begin with the graph of y is equal to sine x. Start off with the simple one. And sitting in here, here's sine graph sitting in here. And I guess, given that all of these start off with your basic graphs, it's important to know your basic graphs. So this is y is equal to sine x, sitting there. Now in this case, it's far easier to work with putting in the n next. So I'm going to look at the graph of sine a half x. So the graph of y is equal to sine 1/2 x, or x on 2, is the graph of y is equal to sine x, the one we just drew. That should say stretched. Stretched by a factor of 2. And again, you might want to think about that just in terms of common sense. For example, I know that the sine of 2 pi is 0, and so sitting in here, when I put 2 pi into sine a half x, I get 2 pi, it's now sine of pi. So what happens at 2 pi in the graph sine a half x actually happened at pi in the graph of sine x. Did I say that correctly? I think I did. Let me say it one more time. What happens at 2 pi in the graph of sine a half x, because 2 pi divided by half is pi, is what happens at pi in the graph of sine x. So everything gets stretched horizontally. So here, this graph did that, comes down to pi. So the graph of sine a half x will get stretched out this way by a factor of 2. So that will be the graph of y is equal to sine a half x. And of course, it would go on indefinitely on both sides. So now I've got the graph of sine a half x, I now have to deal with this pi on 4 bit. And I guess just before I do that, notice that the period of this function is 2 pi divided by a half, so it's actually 4 pi. So this one has, this period of this graph is 2 pi divided by a half, that's 1 on 2, and so that is 4 pi. Hence the graph is stretched horizontally. So now I come to finding the graph of a half x minus pi on 4, or x on 2 minus pi on 4. This is the graph of y is equal to sine a half x. Now because this is minus, it's going to shift to the right rather than to the left. Shifted to the right by, and it's not going to be pi on 4, it's actually going to be pi on 4 divided by a half, and that is pi on 2 units. And I don't know if this is going to be helpful or not, but let me try it anyway and see how we go. So in here, if I just scribble here for a bit, if I have function x is sine nx, and then I go function x plus k on n. We know that the graph of function x plus k on n shifts the graph to the left by k on n units. Agreed? Now, in this case, sine of function x plus k on n is n times x plus k on n, which is, when I multiply in here, nx plus k. So the graph of sine nx plus k is the graph of sine nx shifted to the left by k on n units. You have to think carefully for a while, but that's how it works. And so that's me trying to explain that thing there. That's why this thing shifts pi on 4 divided by a half units. It shifts by that amount, k on n. I'll let you ponder that for the moment. But what that means in terms of my graphs is that I now have the graph of sine a half x. I now have to shift it to the right by pi on 2 units, and it now goes like this. Down here. And so this will be the graph of y is equal to sine x on 2 minus pi on 4. And we can see either from the formula here that the A is 1, or from the graph that it goes between -1 and 1, that the amplitude is 1, and we've already worked out that the period will be 4 pi, because that was the period of sine a half x, and all we did was shift that along the graph a little bit. And so there's our period and amplitude for this generalised trig function. As I think I say to you with nearly everything that I explain, all of this becomes better if you practice. Okay? Unfortunately, there is just no substitute for it. The more you practice, the more you struggle, the better you'll actually end up handling it. Hopefully, if you have a lot of trouble with it, you actually get hold of your tutors, your workshop demonstrators, or the past people and sort them out. Now, I noticed in the notes that that particular example had another way of doing it. So I'll just quickly go through this way. I don't think it's any better or any worse, but what it did was it said begin with the graph of sine x again. So begin with y is equal to sine x. Actually, I'm not even sure. Anyway, we'll do that. Here it is sitting here. Here's the graph of... Oops, it goes up here. Here's the graph of sine x in this one. There. So that's the graph of sine x. Then... Oh. I see. I'm in the wrong spot. Doesn't matter. But anyway, note, here's the next thing. Here, f of x is sine of x on 2 minus pi on 4. And we can write that as, if I take the n, in this case a half, out, I can write that as x minus pi on 2. So that becomes a half x minus pi on 4 if I multiply the half in. And then, according to the notes, you can recognise straight away that the amplitude of this is going to be 1, the period is going to be 2 pi on n, and the thing will be shifted to the right by pi on 2 units. So the actual number of units you shift to the right is actually sitting in your formula. And so long as you remember what each of those things do, you can read it straight off from that. So this says, therefore the amplitude is 1, the period is 2 pi on a half, which is 4 pi, and the graph is shifted to the right. And I guess in there I should have said, because you still need this, you still need the graph of y is equal to sine a half x. The graph of y is equal to sine a half x shift to the right by pi on 2 units. And so you can actually read all of that off from that way of writing the function. So if you like to do that, by all means do so. And so sitting there, so I still had to draw the graph of sine a half x to know where to shift it. And so here's the graph of, comes through here like this. Here's the graph of sine, there we go. That way it's obvious that it's period 2 pi. So that one is the graph of y is equal to sine a half x. one's the graph of sine x. And now I shift that pi onto further over. So it looks like this. I'll make it look the same. Here it comes. Like that. So that's the graph of sine a half x minus pi on 4. And that's the same graph we had before. I've just got a different scale here. I've gone out further. I've actually gone out to the 4 pi in that particular picture, is all. So that graph and the one I've got here are the same. I've just got a different scale sitting the other way. I've scrunched it all up. Get the same graph. So I imagine if you got really familiar with these things, doing this and writing it this way is quite quick because you can see straight away what you've got to do. The other way is more systematic, if you like. I don't mind either way as long as you can get it all out. Alright, so that's as hard as we're going to get in terms of trig graphs. In terms of overall concept, the idea is the trig functions are used for modelling stuff that's periodic, and the general trig functions means that I can model all sorts of different things. Right, that's the big picture.